Hey everyone, welcome to this explainer. Today, we are diving into literally one of the most paradigm-shifting research papers in the modern history of artificial intelligence. Attention is all you need, published by researchers at Google and the University of Toronto. If you've ever found yourself wondering how modern AI systems process language so flawlessly, well, this is the foundational architecture that started the whole thing. We're going to break down all this complex math and these big concepts into a really clear journey.
To kick things off, just picture this. What if an AI could read an entire book all at once, instead of just plodding along word by word? Up until this paper dropped, machine translation and language modeling heavily relied on models that had to process information in a really strict sequential order. But what if there was a way to completely break that bottleneck? A way to let a system look at everything simultaneously? That is exactly the revolution we're about to explore.
So here is our roadmap for today. We're going to cover 1. The sequential bottleneck. 2. The transformer architecture. 3. The attention mechanism. 4. Multi-head attention. And 5. Unprecedented performance gains.
Let's jump right into Section 1, the sequential bottleneck and the limits of time and memory. Before we can really appreciate the genius of the transformer, we have to understand what older AI models were fighting against. Before this paper, the absolute state-of-the-art for sequence modeling was recurrent neural networks, or RNNs. The big constraint here is that they align positions to steps in computation time. Essentially, an RNN generates a sequence of hidden states by looking at the previous hidden state plus the current input. It has to read step 1 to understand step 2 and step 2 to understand step 3. It inherently makes it impossible to parallelize the work. So when you're dealing with really long sequences of text, memory constraints kick in and things basically grind to a halt. What the researchers proposed represents a massive mathematical leap. Those older sequential models, they required O of n sequential operations. That means the processing time grows linearly with every single word you add. But this new self-attention model connects all positions with O of 1, a constant number of sequentially executed operations. It fundamentally removes the limits of time and memory that held all those previous models back.
That takes us to Section 2, the transformer architecture. This is a true paradigm shift.
This brilliantly designed architecture completely throws out recurrence and convolutions. We have an encoder stack and a decoder stack. Now, most competitive neural sequence models use an encoder-decoder structure, but the transformer implements it entirely differently. It relies completely on stacked self-attention and point-wise, fully connected layers. There are absolutely no RNNs in sight here.
So how does data actually flow through this geometric masterpiece? First, the encoder maps an input sequence, let's say a sentence in English, to continuous representations, and it does this completely in parallel. Second, the decoder takes those representations and autoregressively generates the output, like the German translation, just one element at a time, basically consuming its own previously generated symbols as extra input. But wait, if we threw out that recurrent step-by-step processing, how does the model know the order of the words? Well, that brings us to step 3, positional encodings. The researchers ingeniously injected sine and cosine functions of different frequencies into the input embeddings. This basically acts as a timestamp for every single word, preserving the sequence order without sacrificing any of that parallel processing speed.
The specific parameters they chose to build this are remarkably elegant. They used a stack of 6 identical layers for the encoder and a stack of 6 for the decoder. They also employ residual connections around the sublayers, followed by layer normalization. This is a neat trick that helps the deep network train smoothly. And across the board, the outputs are standardized to a dimensionality of exactly 512. It's really this strict, uniform simplicity that makes this deep network so incredibly robust.
Now we arrive at Section 3. This is the absolute core of the paper, the secret superpower, the attention mechanism.
So, what does attention actually mean mathematically speaking? An attention function simply maps a query and a set of key-value pairs to an output. Think of it kind of like a retrieval system. The query is what you're looking for. The keys are the labels on your filing cabinet, and the values are the actual contents of the files. The output is computed as a weighted sum of those values. It allows the model to draw global dependencies. It literally learns which parts of a sentence it should attend to or care about, regardless of how far apart those words are in the text.
But the researchers didn't just stop at one attention mechanism. Let's move to Section 4 to see how they leveled this up with multi-head attention.
First up, we have scaled dot product attention. This is where those queries, keys, and values are multiplied together,
scaled down by the square root of their dimension to keep gradients from vanishing, and then passed through a softmax function to get the weights. It is incredibly efficient because it uses highly optimized matrix multiplication code. But the real magic happens when they scale this up with multi-head attention. Instead of just doing this once, they linearly project the queries, keys, and values into multiple dimensions and run the attention function in parallel 8 separate times.
Now, why do this 8 times in parallel? Because it allows the model to jointly attend to information from completely different representation subspaces. Think of it this way. Using multiple heads is like having 8 different brains reading a single sentence at the exact same time. One brain might be looking for grammar, another for the emotional tone, another for the relationship between the noun and the verb. Because they are running in parallel and then combined together, the model builds an unbelievably rich, multidimensional understanding of the input.
All of this elegant architecture and brilliant mathematics is fascinating, but does it actually work in the real world? Let's get into Section 5, Unprecedented Performance Gains.
When this paper was published, it absolutely shattered existing benchmarks. On the standard WMT 2014 English to German translation task, previous state-of-the-art models like ByteNet scored a 23.75. A massive GMT ensemble model, meaning multiple models mashed together, hit 26.30. But the single big transformer model, it established a new state-of-the-art score of 28.4. Beating the best ensembles by over 2 full blue points is just a massive leap in translation accuracy.
And the transformer didn't just win on accuracy, it completely rewrote the rules on computational efficiency. If you look at the training cost comparisons measured in floating point operations, or flops, previous ensemble models required a massive 10 to the 20th or 10 to the 21st power. The transformer achieved its superior score requiring only 10 to the 18th or 10 to the 19th flops. That is a tiny fraction of the computational training cost of the very models it was beating.
Which leads us to one staggering number, 3.5 days. Because the transformer threw out sequential recurrence and allowed for massive parallelization, they were able to train the state-of-the-art model in just 3.5 days using only 8 P100 GPUs. For some context here, older models could take weeks or even months on far more expensive hardware setups. In the English to French task, this quick 3.5-day training run yielded an unheard-of single-model blue score of 41.0. High performance, low training cost, incredible speed.
I want to wrap up this explainer with a quote straight from the conclusion of the paper itself. The researchers wrote, "We plan to extend the transformer to problems involving input and output modalities other than text, such as images, audio, and video." Keep in mind, this was published back in 2017, and it is just an incredibly prophetic statement. By proving that attention is all you need, they laid the exact groundwork for the multimodal AI revolution we are literally living in today. From the large language models writing our code to the AI generating our images and video, it all traces back to this very architecture. So, the question to leave you with is this. Now that the sequential bottleneck is broken, what complex dependencies will transformers learn to solve next? Thank you so much for joining me for this explainer, and keep learning.